All right, so this last problem that we're going to do in 9.5 is another mixture problem. It's one that it's a type of problem that we've done before. We did this in 9.3, and we set up a mixture problem that gave us a separable equation. Now, what made that one separable, it turns out, was the fact that the inflow and the outflow rates were the same. We had fluid flowing into a tank at a particular rate, but the mixture was flowing out of the rate at the same time, which means the volume of the fluid in that tank was never changing. That ended up giving us a separable differential equation. It turns out if those two rates are different, the dE will no longer be separable. So we want to look at a case like that. So here's what we have. Initially, a tank contains 10,000 liters of brine with a salt concentration of 1 kilogram of salt per 100 liters. Brine with 2 kilograms of salt per 100 liters leaves the tank at a rate of 20 liters per second. The well-stirred mixture leaves at a rate of 10 liters per second. So find the concentration of salt as a function of time. This time we're not looking for the actual amount of salt at a given time. We just want the function y of t that gives me the amount of salt at any given time. So notice that the inflow and the outflow rates are different. We have solution, or we'll call it brine, actually they call it brine here, flowing into the rate of the tank at 20 liters per second, but only flowing out at 10 liters per second. So those don't match as far as the rates are concerned, which is fine, but you're going to see that we can't solve this using separation of variables anymore. So when we're setting up our differential equation, remember we want to have an inflow rate and an outflow rate. So the inflow rate, first we should look at the concentration of the salt in the brine before applying the actual rate at which it's flowing in. So we have 1 kilogram of salt, 1 kilogram, for every 100 liters. So this is the concentration of salt in the brine. It's not the inflow rate yet. We need to multiply that by the rate at which this solution is flowing into the tank, which is 20 liters per second, or 20 liters for every 1 second. Okay? And if we do this correctly, liters should cancel each other out, giving me a unit of measure that's kilograms per second. That's the rate at which salt specifically is entering this tank. Okay? So when I do this, when I multiply these together, I get 20 over 100, which... let me make sure I have the right thing here. Oh, I'm sorry. I gave the wrong value here, though. I was reading... I'm sorry. I'm using the initial concentration of salt in the tank. What I needed was 2 kilograms of salt per 100 liters, because that's the rate at which it's entering the tank. This is just where we're starting at. That should be a 2 right there. Let me fix that. When you multiply this out, you're going to get 40 over 100, which simplifies to 2/5. So our inflow of salt is 2/5 of a kilogram per liter. Per second. The liters canceled out. Okay. So every second, 2/5 of a kilogram of salt are entering this tank. We need outflow as well. What is our outflow rate? Okay. So once again, we need a concentration of the mixture that's leaving the tank, and then we need a rate at which it's flowing out of the tank, which multiplies with that. In this case, the concentration won't be a constant because the amount of salt in the tank is changing over time. So I don't know that it's a constant 2 kilograms or 100 kilograms or anything like that. But that's what our function y is supposed to tell us. Remember, y represents the amount of salt in the tank at any given time. So y kilograms, okay, divided by the amount of brine in the tank. That's how we find a concentration. The amount of salt divided by the total amount of liquid in the tank, which is what brine means. But the amount of liquid in the tank is actually also changing over time. We know that we start with 10,000 liters. But then as time passes, the amount of brine in the tank is actually increasing. And the reason why is because we have a solution flowing into the tank at a faster rate than it's flowing out. So the volume of that brine is going to increase over time. But by how much? Well, if we have brine flowing in at 20 liters per second, but then flowing out at 10 liters per second, then the actual increase each second of brine in the tank is going to be 20 minus 10, which is 10. But for each second that passes, which is what our variable t represents. Okay, so our denominator here is a little bit more complicated as well. It's not just a constant, it's a linear function because we have a volume of water that's changing over time. Now the units here would be liters. So now I need to multiply that by my rate at which this fluid is flowing out, which is 10 liters per second. And the liters will cancel. The 10, I can divide these things by 10 for some cancellation there. I'm going to get y over that 10,000 will become 1,000 plus just t now. And that would be kilograms per second. So that means my rate of change of salt in the tank, which is dy dt, remember that's equal to my inflow rate minus my outflow rate. So 2/5 minus y over 1,000 plus t, which notice if I move this term over here can be written as dy dt plus 1 over 1,000 plus t. And sorry, my plus and my t's look really similar. So that's not a t or a plus plus, that's a plus t right there. Times y equals 2/5. So if you notice, I just added this term over and I wrote it slightly differently. Okay, this is a linear differential equation and it's in the form that I want it to be in. dy dt plus some function of t. It's not a function of x anymore, we're using t. Y equals some other function of t. Now it's a constant, but you can think of constants as constant functions. So that thing right there is like p of t. Okay, that's the thing that's going to be used when I find my integrating factor. Let's do that next. My integrating factor, which now it's a function of t, not x, is equal to e to the power of the integral of that p of t function. So that's 1 over 1,000 plus t. dt over 1,000 plus t. Okay? Now that I'm going to get a natural logarithm, e to the natural log of 1,000 plus t. Normally you would put absolute value bars here. I don't need to do that since time can't be negative in this problem, so 1,000 plus time is always going to be some positive number. The e and the natural log cancel, and I get 1,000 plus t as my integrating factor. So now we need to take this dE up here, multiply both sides of it by 1,000 plus t. That is going to look like this. 1,000 plus t times dy dt plus, when I multiply this guy by 1,000 plus t, it just cancels that 1,000 plus t in the denominator and gives me a y, which is kind of nice, equals 2/5 times 1,000 plus t, and I'm going to distribute that 2/5 in. That's 400 plus 2/5 t, okay? So now I want to represent this thing as a derivative, and remember, if this is y and that's dy dt, then I'm thinking of this thing as mu, which means I'm multiplying this y by the derivative of that. And the derivative of this is just 1, which is what I see in front of that y. So I can write this as 1,000 plus t times y, and then all of that prime, because again, that's like the product rule. And I set that equal to this version of this expression here. So 400 plus 2/5 t. Now is the step where we integrate both sides, this time with respect to t. Make sure you put parentheses around these because there's more than one term there. Okay? That is going to give me this. 1,000 plus t, y equals, this is a pretty straightforward integral, 400t plus 1/5 t squared plus c. Okay? Now I can solve that for y. So that y is equal to 400t plus 1/5 t squared plus c all over 1000 plus t. Now we're not done because I need to know what c is. So coming back up here, is there an initial condition I can use? Well, it says that initially the tank contains 10,000 liters of brine with a salt concentration of 1 kilogram per 100 liters. I don't want to know how much brine there is. I only want to know how much salt there is initially. So what that is y of 0 equals, I have 10,000 liters of brine altogether, but the concentration of salt in there is 1 kilogram of salt for every 100 liters. So 10,000 liters there, 100 liters there, 1 kilogram of salt. Liters are going to cancel, and this is going to end up giving me 100, is that right? Yeah, 100 kilograms of salt at time 0. Okay, so that gives me an initial condition that I can use to then try and solve for c. Let's do that down here. So if I use my initial condition, I'm setting y equal to 100 now. And this would be equal to this guy once I plug a 0 in for t. But these two terms will go to 0, just giving me a c in the denominator. This guy down here is going to become 1,000 plus 0, so just 1,000. And I can multiply both sides by 1,000, so that c is equal to 100,000. Okay, now that gives me this as my final answer. Y is equal to 400t plus 1/5 t squared plus 100,000 all over 1,000 plus t. Okay, so again, we can solve these mixture problems even if they don't come out to a separable DE, because in cases like this, they will oftentimes come out to linear differential equations, but now we know how to solve those. Okay, so that's going to wrap things up for Chapter 9.